So I'm going to talk about actually three things, but the overarching theme for all of it is what about confronting our exascale software challenges, right, with a focus on the programming models and some of the solutions that we're looking here in chemistry. And what you'll see is some of the challenges we've got are kind of different in chemistry from the sort of more traditional engineering domains, and that's led us over the years to actually adopt much more aggressively code generation and code transformation techniques. So the first thing I want to start off with is a description of the NWChemEx project. So NWChem, now nearly 25-year-old, massively parallel chemistry code coming out of Pacific Northwest Lab, hence the NW. And basically the realization, as probably is the case for nearly any domain, that we're going to have to essentially completely redesign and re-implement this to get to exascale, because our ability to take the concepts and programming models, design points that were relevant in the late 90s and 2000s to the exascale era, right? That's basically broken a lot of our design. Here's the team. It's a large team spanning 6 national labs, and then also with a footprint of Virginia Tech, where we have Ed Valeev, a very talented computational chemist. And as you can see, we sort of span all the space in the traditional sort of model for computational science in a sort of SIDAC sense. What are our problems, right? So again, why are we doing exascale? It's all about the science. And we tie very closely into the missions of biological and environmental research, BER, basic energy sciences, BES, 2 offices within the DOE Office of Science. And the 2 main challenges that we're focusing the initial development on are efficient production of biomass, which is basically sustainable energy production technology. And for that, we really need to get down to the point where we can have quantitative modeling of what's going on at the membrane level of cells and crops, and then converting that biomass into fuels, right? And that fuels and other chemistries, right? And that involves understanding all sorts of details of large molecules. And what we have, a common thread between them, are basically the desire for high accuracy that spans both large timescales and large length scales. And these are things that are challenges to us as computational chemists, for reasons I'll explain briefly. We want quantitative thermochemistry, but ultimately we need more quantities than that to make contact with experiments. So we're anticipating also delivering spectroscopies, all of the other properties that chemists use when they're trying to understand what's going on in a system. These are the sort of scales of systems that we need. And one of the main challenges that I'll talk about is the fact that our methods, as formally developed, scale very non-linearly with the size of the system. And there's big consequences to that. So if we magically waved a wand over NWChem as it is now and re-implemented it with a modern architecture and modern C++ and all of the good technologies that go with that, what are our main challenges that are left, right? And this is roughly in order of decreasing risk as we think about the project. The main one, obviously, is the programming model. How do we express, in hopefully a performance portable way, our intent, right? How do we go from intent into algorithm into actual implementation? I'd say for some of our space, we don't understand how to do that. For other parts of our space, actually, we've got very good exemplars that make us confident that we're going to be able to meet these goals. A key aspect of this is maintaining productivity. So for us, we're not thinking about exascale as a point in time. It's not the first exascale machine. We're entering an era. We're thinking about exascale being a path into the future. And so we have to prepare ourselves to be scientifically productive along that entire path. So it's not about hero calculations on the first exascale machine. It's about science going off into 2030. You can think of that as the lifetime of NWChemEx. We clearly need strong scaling, both to use the capabilities of the machine, but also to meet our science objective. A lot of chemistry is tangled up not just in the energies, but also in the entropy. And the entropy is mainly the dynamics, the motion of the molecule over long periods of time. So So we need to capture those dynamics, but again, we need to do it using accurate energetic technologies. We need to have reduced scaling. I'll talk about a bit more of that on the next slide. But a key thing about this is we need to do this with good error control. There are lots of heuristics in place right now for getting reduced scaling methods at the price of uncontrolled errors, but clearly that's not satisfactory. So basically there's a proof of principle understanding how to do all of these things, but no one's yet assembled all of these capabilities into a code that can also execute at full scale. And so we need to put all of, essentially the activities of an entire decade's worth of the community together. Another aspect of quantitative science is eliminating and controlling other sources of error. And for us, a major source of that error is basis truncation. A molecule is made up out of atoms, and so a very good approximation is to assemble your molecular wave function from a bunch of basis functions centered on the atoms. That's the mainstream representation we have in chemistry. So working towards complete basis sets that eliminate that basis set error is a key point. That involves lots of numerical challenges. And there's a companion error that's associated when we go from one electron models into many electron models. And there we have to explicitly incorporate electron correlation in a more direct way. Here, basically, our initial priorities. If we look here at the reduced scaling, right, this is explaining why we have to emphasize reduced scaling methods. Our gold standard for chemistry scales as the 7th power of the system size. And so if we allow for a factor of 1,000 increase in machine performance, but with an n to the 7th scaling algorithm, we're only going to see a 2.7-fold speed up in the size system we can simulate, right? Similar sort of increase in the accuracy will be possible as well, right? Clearly, we need to push into this regime, right? We're not going to get to linear scaling because that's, in a theoretical sense, not strictly possible while we maintain good control of the error. So we're going to be somewhere, depending on the accuracy that you want and the level of theory that you're using, we're going to be somewhere in this regime. This is some slices through our software stack. It's complicated and evolving. Basically, LCAO, the linear combination of atomic orbital approximation that I mentioned here, it's built on this stack here. TAM down here is a tensor library for many-body methods, and it's our main tool. And I'm going to talk about this a little bit more on the next slide, but basically takes a high-level specification of our problem, translates that into, in part statically and then in part at runtime, into calls into libraries that are automatically generated by a bunch of other tools, some of which are coming from elsewhere in the Exascale software stack, and then maps into XGA is the Exascale Global Array project, and then a bunch of low-level runtimes below that. One key aspect of the complexity is navigating the more complex memory hierarchies and recognizing that's where a lot of performance and also energy consumption goes. And so at the same time as we're working towards driving these many-body compute technologies into Exascale and to handle the reduced scaling algorithms that are much more complicated than the older dense algorithms, we have to navigate mixed precision and also potentially computing with compressed data. And we see lots of potential in that, but obviously we've got to be careful. This is an example of the input to this tensor application. It's actually just a snippet of a description of, I think here, a couple cluster singles and doubles algorithm. The actual full specification is probably about 10 pages that look like this. And that's the simplest model that we have, right? So imagine this model now where you're asking to include the effects of different types of correlation, and you want to look at an excited state, and you want to calculate gradients. You've suddenly gone from 10 pages of input into hundreds or thousands, right? And that's why we as a community transitioned some time ago from basically manually writing code into using interpreted high-level spec, right? this code's already been processed by 2 other steps. It was basically generated initially by something that processes things that look like Feynman diagrams. That then gets shoved into a tool called opmin that is part of a collaboration with Sadi Yapan at OSU. And that does an operation minimization that looks at memory usage and computational cost and basically tiles everything up like this, extracting common intermediates and everything. And then this is basically what gets interpreted and run at runtime. So that's where we're going. I'm going to segue briefly to discuss what's our connection with MolSSI. You heard Dan Crawford talking about that this morning. It's a very exciting project for me to be involved in. And it's clearly got a lot of synergy with NWChemEx and vice versa. And so this slide is sort of like stating something that's very familiar to everyone in the room, right? There's no such thing as a sequential computer anymore. There probably never was, maybe since the Intel 88 or something. But you can see we have to express massive amounts of parallelism. And we as a community, thinking about computational chemistry, really are very much unprepared for that, right? Computational chemistry right now, as is material science, is largely a cottage industry, right? The main intellectual innovation is happening in small university groups, single PI activities. We have to connect those into a collective effort so that those ideas can get collected into these larger community codes much more effectively. And another aspect is the longevity of this code and the understanding of the community about what computers and software should look like, right? That code will live a long time, 10 to 20 years, but people's understanding of computation out there in the wild world is probably 10 years out of date. Okay? So that's a big part of what MolSSI has to do, and that's part of where we at NWChemEx interfaces with MolSSI, right? So we can assist in a lot of the training and workforce development parts of their mission, and they also can leverage from our expertise and interest in high-end computing. Now, MolSSI is interested in much more than just exascale computing. It's serving a much larger community, interested in computation going all the way from apps on cell phones up to supercomputers. In the interest of time, I'm going to keep moving. I'm going to spend the last few minutes talking about a related project. So Madness slots in essentially alongside NWChemEx in terms of some of the numerical methods and some of the runtime capabilities. But Madness is an environment that I've been developing for some years now in collaboration with other groups in the US and then in Japan and Europe. And so it's started out as a tool to address some of the numerical and computational problems in chemistry. So why are our codes, why is our software so big when we can write the PDEs or whatever that describe our equations in a much more compact manner, right? That's the semantic gap that Phil Colella talks about. Why is it that they scale, our algorithms scale nonlinearly with the system size, right? So computational chemists have a very sad claim to fame, right? So standard computational chemistry Gaussian basis set solves Poisson's equation in time that's quartic in the size of the system, right? Instead of linearly, right? We all know we can do linearly. And that's because of the choice of representation. And so a compact representation, right? Back when computers were graduate students chained to their desk, right? You needed a compact representation, and these atomic orbitals do that. But now we've got computers that can handle lots of data, right? Simpler basis functions that you can compute more rapidly with, but you have more of them, actually have lots of advantages. And so we want fast algorithms that have strong error control. This is just an example, basically illustrating how it's a little different computing in Madness than in say, a standard certain chemistry code. We specify the problem. Here we're basically doing nothing interesting. We're just calculating the electrostatic potential due to a Gaussian, right? So trivial. So here we have a specification of the problem. We specify the accuracy that we want to compute to the domain. Here's the Gaussian specified analytically. These two are the only lines doing anything. This projects into the numerical representation. And this line here solves Poisson's equation, but not by iterative solution of Poisson's equation, the differential equation. It actually directly applies the Green's function. And so we're using techniques for multi-resolution analysis to do that. And so here's some of the math that's sitting behind madness. The multi-resolution stuff is up here, where we basically understand the behavior of functions and operators, looking at the difference between length scales. And what we're doing here is basically translating smoothness into sparsity, right? You can look at this as a standard adaptive mesh approach as well, but looking at it from this perspective also gives us a constructive approach to accurate and fast application of integral operators. So a key component is that everything is done to finite precision, right? It's not just that we're throwing away numbers less than some threshold. Each individual number is only computed to the precision that we're interested in as well. So that is a potential lots of speed that we're getting out of this, but it also makes the numerics and the dynamics of the code quite different, and in particular gives us very dynamic and irregular computation. There's a challenge for some styles of composition. So here's the Madness software stack. I'm not going to talk about this. I'm going to talk a little bit about here, and in particular to use it as an opportunity to whine a bit about task-based programming. Because a lot of people are looking at that as that's their savior, and my message is, you got to, this is a horse that you need to look in the mouth. Right? So we started off doing Madness like 15 years ago, so really the push here was to get it onto the craze of that era. And we wanted to make the numerical layer of Madness easier to write and to handle all of the complexity from this very irregular computation. And over the years, it's tied into lots of other projects. There's a bunch of elements that we sort of stack together. Underneath everything, we have some one-sided active messaging. We have futures that we use to manage asynchronous computation, essentially latency, whether it's coming from a dependency that's not yet satisfied or some communication or I/O or anything. We construct global names and namespaces that span the machine, so an application can be composed in terms of names that make sense to it instead of pointers and process numbers. And let me keep going. So the simple model that we have inside a single process is there's a logical main thread for the application, and essentially all concurrent computation is achieved by submitting tasks to the task queue, and then there's a separate thread that's handling requests, tasks, or requests for data coming in from other processes. So yeah, there's an interface that defines a task, and you can submit tasks locally or remotely. And we use a lot of C++ templates to basically manage a lot of the complexity and make it easy and intuitive to write this stuff. And so we had lots of successes, right? We were initially, I think, very happy with tasks and had very good experience, especially, again, for our regular workload. And interfacing them with futures really worked out very well, again, at the beginning. But we can have a long list. Actually, the list you can see is even falling off the end of the projector. So there's a bunch of things that really get in the way of making this a scalable solution over the long term. And one of the problems, perhaps the main problem, is once you start composing with tasks, right, your tasks are basically fundamental units of computation that can't block, right? Things that block need to be coming in as arguments. So if you've got a piece of code that, this wants some data from here, this wants some data from there, this needs this computation to happen first, right? You have to divide it up into all of these chunks. Unless you've got a compiler to do that for you, right? You've got a lot of manual partitions that you're injecting into your code. And that is very labor intensive, and it starts obscuring the intent. And then eventually it ossifies into your code, right? Design decisions that you've made that are hard for you to back out of. And if you don't have an intelligent runtime sitting behind your task system that is actually aware of the underlying data stores and everything, it's very easy to express task-based computation and then drown in the data motion and everything that you just triggered. So I think I've got some comments here about really what's needed to make task-based computation practical, and there's some exemplars out there. what we're doing is actually under some NSF funding is collaborating with a team that develops parsecs. So this is the team in Jack Dongara's group at the Center for Innovative Computing at the University of Tennessee, so George Basilka and Thomas Aroux, and then Ed Valleev at Virginia Tech. So parsec is basically the DAG-based task-based runtime engine that sits beneath the next generation of parallel linear algebra. So the motivation for the project was saying, hey, this tool has demonstrated great success in linear algebra. It's going to be everywhere. It's going to be maintained and grow. And so what we want to do is work with them to extend what they do to be more relevant to us. And presently, the main drivers for parsec have all come from dense linear algebra, right? Where there's essentially no data dependencies in the DAG. The DAGs look the same. They just get increased by scale as you increase the size of the matrix. So our main focus working with them is to extend their runtime structure and also their API so that it accommodates our more irregular style of computation. Let me hop forward here. And so basically, parsec's model is, you can think of it as a templated task graph. You express a dependency between computational steps, and each computational step is essentially parameterized by a key. You can think of it as maybe the iteration in a for loop or something. For us, it might be the node in the tree that we're traversing. So the actual graph, the actual DAG, if you expanded it out of the tasks, you might have billions of these things. You can't manage that DAG. But by having this parameterized DAG, you've now got something that you can manipulate both statically and at runtime. So it's much more scalable and potentially efficient. So really our goal is to implement, once this API layer is finished, is basically to layer a code generator that maps onto it. I think I maybe skipped over a slide that indicates we've got collaborations with other dependency-style programming models that would include Legion, CNC, and then through NWChemEx with the Dharma team. So I'll wrap up there. So thanks very much.
Deep learning efforts that are going on, like what Adrian Reutberg and those guys are doing, trying to connect those, and then what Fred Streitz and the other labs are doing for the extreme scale type of simulations, and then how you're looking at that scaling and accuracy. It's kind of like how all of that kind of comes together with all the efforts.
It comes together in a variety of ways. So I didn't touch on how we interact with sort of exascale era workflows, but that machine learning application would be one of those. And what's happened really over the last 15 years or so in chemistry and material science is we transitioned from an era when calculations were run one at a time by a grad student writing an input file, run the calculation, read the output, into a mode where most computation is driven by automated searches and optimization techniques. That's probably 99.9% of computation is now like that. And so there are workflows that tie into very large databases. I guess, for instance, the solar cell activity up at Harvard and MIT is a good example of that. The connection, were you referring to the Exascale Co-Design Center when you said Fred Streitz?
No, the large-scale simulations that they're trying to use, basically for the simulation to have the deep learning or some sort of machine learning come back into it to have this iterative process.
That ties in, for us, that ties in the external workflow, right? So I think once we get down into the equations that describe our physics, so this is basically quantum electronic structure, there's no free parameters to futz around with here, right? So we basically get told, here's a molecule, here's the structure, compute the whatever property we were asked for.